Equilibrium. The next chapter is called chemical equilibrium. When a liquid evaporates in a closed container, the molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase. See, and the number of liquid molecules forms a vapor phase strike the liquid surface and they retained in the liquid phase. So it gives rise a constant vapor pressure because of an equilibrium in which the number of molecules leaving the liquid equals to the number of returning to liquid form the vapor. So we say that this is the system is reached equilibrium state. So at this stage, this is not static equilibrium and there is a lot of activity at the boundary between the liquid and the vapor. Thus, at equilibrium, the rate of evaporation is equal to the rate of condensation. Look at this. This H2O liquids goes H2O vaporization. That is the double half arrow indicates the process both the direction are going on simultaneously. So the mixture of reactants and the products equilibrium state is called equilibrium mixture. So when the equilibrium can be established for the both physical process and the chemical reaction. The reaction may fast or slow depending on the experimental condition and the nature of the reactants. When the reactants in a closed vessel at a particular temperature react to give products. So the concentration of the reactant keeps on decreasing while the concentration of the product keeps on increasing for some time. After which there is no change in the concentration of either reactant or product. So this stage of system is called dynamic equilibrium. See, and the rate of the forward and the reverse of reaction becomes equal. It is due to the dynamic equilibrium stage that are no change in the concentration of the various species in the reaction mixture. That is based on the extent to which the reaction proceed reach the states of chemical equilibrium may be classified in this group. First, the reaction proceed nearly completion. This means the reaction that proceed nearly completion and only negligible concentration of the reactants are left. In some cases, it may not be even possible to detect these experimentally. Then, second, small amount of products formed. This means the reaction in which only small amounts of product are formed and most of the reactant remains unchanged at the equilibrium stage. Then third one is the concentration of the reactant and products are comparable. This means the reaction in which the concentration of the reactants and the products are comparable when the system is equilibrium. The extent of the reaction equilibrium varies with the experimental conditions such as concentrations of the reactant, temperature, like this. So the optimization of the operational condition is very important in industry and laboratory so that the equilibrium is favorable in the direction of the desired product. Then next is the equilibrium in physical process. Equilibrium in physical process that better understood if we examine some physical process. That is, the most familiar examples are phase transformation process. The phase transformation means solid liquid, liquid to gas, solid to gas. So these are the phase transformation reaction. So usually the first solid liquid equilibrium, liquid vapor equilibrium, solid vapor equilibrium. First we will discuss the solid liquid equilibrium. Ice and water. Suppose if you take ice and water kept in a perfectly insulated thermoflask at 273 Kelvin and the atmospheric pressure on the equilibrium state and the system shows interesting characteristics feature. We observe that the mass of ice and water do not change with the time and the temperature remains constant. However, the equilibrium is not static. The intense activity can be noticed at the boundary between the ice and the water. So, ice and water. So here, however, the equilibrium is not static. That is, I think molecules The molecules from the liquid water collide again ice and other to it, and some molecules of ice escape into the liquid phase. There is no change of mass of ice and water, as the rates of the transfer of molecules from ice into water and the reverse transfer from the water into ice are equal at the atmospheric pressure as 273 Kelvin. So it is obvious that ice and water are in equilibrium only at particular temperature. That is 273 Kelvin. 73 Kelvin. For any pure substance at atmospheric pressure, the temperature at which the solid and liquid phase are at equilibrium is called normal melting point and normal freezing point. Normal melting point and normal freezing point. So that is freezing points of the substance. See, usually the system here, the dynamic equilibrium and can following, that is both the opposing process occurs simultaneously, ice and water. That's mean both opposing process occurs simultaneously. Both the process occur at the same rate, so that the amount of ice and water remains constant. So this is called solid liquid equilibrium. Next is liquid vapor equilibrium. See, this equilibrium, that is liquid vapor equilibrium, can be better understood if we consider the example of a transparent box carrying U2 with mercury. Mercury drying agent like anhydrous calcium chloride or in phosphorus pentoxide. It is placed for a few hours in the box. After removing the drying agent, by tilting the box on one side, a watch glass containing water is quickly placed, that is quickly placed inside the box. It will be observed that the mercury level, yes, look at this is the mercury level. The mercury level in the right hand limb of the manometer slowly increases. See, look at this mercury level and this mercury level slowly increases and reaches the constant value. Also, the volume of water watch glass decreases. So, volume of water watch glasses also decreases. So, here initially there was no water vapors inside the box. As water evaporate, the pressure in the box increased due to an addition of water molecules into a gaseous phase inside the box. So, the rate evaporation is constant. However, the rate of increase in the pressure decrease with the time due to the condensation of vapor into water. Finally, it leads to an equilibrium condition when there is no net evaporation. That's mean this implies that the number of water molecules from the gaseous state into the liquid state also increase till the equilibrium is attained. So the rate evaporation is equal to rate condensation. Rate evaporation is equal to rate condensation. So here that's mean the H2O liquid, H2O to vapor. So at the equilibrium, the pressure exerted by the water molecule at a given temperature remain constant and is called the equilibrium vapor pressure of the water. So vapor pressure of water increase with the temperature if the above this experiment is repeated with methyl alcohol, acetone and ether. It is observed that the different liquids have different equilibrium vapors pressure at the same temperature, and the liquid which has the higher vapor pressure is more volatile and has lower boiling point. Then the solid vapor equilibrium. Solid vapor equilibrium. See here, let us now consider the system where solids sublimate to vapor. If we place a solid iodine in a closed vessel, that is iodine in a closed vessel, after some time the vessel gets filled up with the violet vapors and the intensity of the color increased with the time. After certain time, the intensity of color becomes constant and this stage is called equilibrium is attained. Hence, the solid iodine sublimates to give iodine vapors That is iodine vapors, and the iodine vapors condense to give solid iodine. So that is iodine solid to iodine vapor. So this equilibrium can be represented like this. This is the other examples showing kinds of equilibriums are camphor solid to camphor vapor, ammonium chloride. This camphor. Other examples mean camphor solid, then camphor vapor, then ammonium chloride NH4Cl, ammonium chloride solid undergoes sublimation reaction to form ammonium, that is ammonium chloride vapor. So these are the solid vapor equilibrium reactions example. The next is equilibrium involving dissolution of solid or gases in liquid. See, first here the solid in liquid and gases in liquid. First we will discuss the solid in liquid. We know from our experience that we can dissolve only a limited amount of salt or sugar in a given amount of water at a room temperature. That is already we know the saturated solution, unsaturated solution like this. If we make thick sugar syrup solution by dissolving sugar at the higher temperature, sugar crystals separate out if we cool that syrup to the room temperature. So we call it that saturated solution when no more solute can be dissolved at the same temperature. So the concentration of the solute is saturated solution depends upon the temperature. So the saturated solution at dynamic equilibrium exists between the solute molecules in the solid state in the solution. For example, sugar solution to sugar solid. So, and the rate of dissolution of sugar is equal to rate of the crystallization of sugar. So, equality of the two rates and the dynamic nature of the equilibrium has been confirmed with the help of the radioactive sugar. If we drop some radioactive sugar into saturated solution of non-radioactive sugar, then after some time the radioactivity is observed both the solution in the solid sugar. See, initially there were no radioactive sugar molecules in the solution, but due to the dynamic nature of the equilibrium, there is exchange between the radioactive and the non-radioactive sugar molecules between the two phases, solid and the solution phase. Sorry, this is solution and this is solid phase. So the ratio of the radioactive non-radioactive molecules in the solution increase till attain the constant value. Then next is the gas in the liquid. When a soda water in a bottle and open means that is some of the carbon dioxide gas dissolved and fizzles out rapidly. So the phenomenon arises due to the difference in solubility of carbon dioxide at the different pressure. There is equilibrium between the molecules of gaseous state and the molecule dissolved in the liquid under pressure, is that is the carbon dioxide gas, then the carbon dioxide in solution. So this equilibrium is governed by the Henry's law. You will learn in next year, that is in solution chapter, which state that Henry's law, mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas at the above solvent. So that this amount of gas, that is the amount is decreased with the increase the temperature. The soda water bottle sealed under pressure of gas, its solubility in water is high. So as soon as the bottle is opened, sometimes dissolved carbon dioxide gas escapes to reach the new equilibrium condition required for the lower pressure, namely it is partial pressure in the atmosphere. So this is how the soda water is in bottle when left open to the air from some time. That turns flat. It can be generalized that means first solid liquid equilibrium, there is only temperature at 1 atmosphere or 1.03 bar at which the two phases can coexist. So if there is no exchange of heat with the surrounding, the mass of the two phases remains constant. Then second, liquid vapor equilibrium. Liquid vapor equilibrium, the vapor pressure is constant at a given temperature. Here the vapor pressure is constant at a given temperature. Then third, for a dissolution of solids, the solubility is constant at a given temperature. So solubility is constant at a given temperature. Then for a dissolution of gas in liquid, the concentration of a gas in liquid is proportional to the pressure of a gas over the liquid. So this means there is liquid vapors H2O. Here some feature of physical process equilibria, that is process and conclusion. Liquid vapors, that is partial, that is pressure of water at constant given temperature. Then solid liquid, the solid liquid melting point is fixed at the constant pressure. Then solute, that is sugar solid, and solute, that is sugar solution. The concentration of the solution, that is solute in the solution, in constant at a given temperature. Then gas of gas and gas of aqueous, that is gas, that is this is constant at a given temperature, and this is also at constant at a given temperature. Then the general characteristics of equilibrium involving the physical process mean the equilibrium is possible only in the closed system at a given temperature. Both the opposing process occurs at the same rate, and there is dynamic but stable condition. All measurable properties of the systems remains constant. When equilibrium is attained for physical process, the characterized by the constant value of the one of its parameters are the given temperature, like this. Then the magnitude of such quantities at any stage indicate the extent to which the physical process has proceeded before reaching equilibrium. So next we will discuss the equilibrium in the chemical process, dynamic equilibrium.